Welcome to This Explainer. Today, we're going to completely flip the way you look at industrial manufacturing. Have you ever stared at a massive chemical plant? You know, the endless maze of pipes, those towering tanks, the hissing steam, and wondered how it all actually works together in real time? Well, we're going to demystify all that complex machinery. We're going to look at a chemical plant not just as a bunch of metal and wires, but as a living, breathing organism. We're talking about its senses, its muscles, its beating heart, and its lungs.
All right, here's our roadmap for today. First, the plant sensory network. Second, valve actuators, mechanical muscle. Third, compressors, the beating heart. Fourth, filtration and drying systems. And finally, number 5, the ultimate industrial symphony.
Let's jump right into part 1, the plant's sensory network.
So to safely control a highly complex process, a plant absolutely has to keep tabs on its analytical variables, just to ensure both purity and safety. You know, it's not just about knowing if a liquid is flowing. It's about knowing exactly what's inside that liquid at any given microsecond. Like, are the chemicals too concentrated? Is the ambient air too humid? Is the mixture getting a bit cloudy? These variables basically tell the plant exactly what's going on in its chemical bloodstream.
Just think about the sheer variety of specialized tools a plant uses as its sensory organs. It's wild. To taste acidity, it uses a pH analyzer to measure hydrogen ion voltages. To sense oxygen levels in, say, a boiler's exhaust, it relies on a paramagnetic analyzer, which literally uses a strong magnetic field to attract the oxygen gas. And to see how clear a liquid is, a turbidity meter shoots a beam of light right into the fluid and measures exactly how much of that light gets scattered by suspended particles. It's an incredibly sophisticated sensory array. But hey, what happens when things get dangerous? Let's say we need to measure the density of a violently corrosive acid. Dropping a standard hydrometer in there? Yeah, that would just leave you with a melted piece of really expensive plastic. Instead, the plant sees the density using a safe external radioactive density analyzer. It just shoots a tiny amount of radiation straight through the thick metal pipe and measures how much is absorbed by the fluid inside. Boom! No physical contact required.
Okay, so gathering all this chemical data is great, but it's really only half the battle. If a sensor suddenly detects an acid spike or a massive pressure drop, how does the plant actually do something about it? How does it translate all this digital, chemical information into physical, mechanical action?
Which brings us to part 2, valve actuators, mechanical muscle.
So, the plant basically relies on two main types of muscle to physically crank open or slam shut these heavy metal doors. Pneumatic actuators are your standard everyday workhorses. They use compressed air to push a diaphragm or a piston. But when the plant needs to force a massive valve shut against a raging, high-pressure tsunami of liquid, it flexes its hydraulic fluid muscles. Since liquid simply can't be compressed, hydraulic actuators deliver way higher brute force without losing any energy to compression.
Now, these muscle systems are engineered for, well, worst case, doomsday scenarios. Let's say the unthinkable happens and the whole plant loses power, or the main air supply lines just snap. What happens to the valves? Well, they rely on built-in mechanical springs to instantly force them into a safe position. If a valve controls cooling water to a vital reactor, it's designed to fail open, meaning if power drops, the spring forces the valve wide open to keep that water flowing and prevent a total meltdown. On the flip side, if a valve controls a highly flammable fuel line, it's designed to fail closed. The spring instantly snaps it shut to stop a catastrophic fire.
While air and fluid offer that great brute force, sometimes you just need the pinpoint precision of electricity. Solenoid actuators act like fast-twitch muscles, while actually more like an instant on-off switch where an electromagnet snaps the valve open or closed in a fraction of a second. Motor-driven actuators are a bit slower, using gears to smoothly dial the flow up or down. But you've got to pay attention to the torque and limit switches here. They act like the plant's nervous system. If a motor tries to force a valve shut, but there's, say, a rock stuck in the pipe, the torque switch senses that dangerous physical resistance and instantly cuts the power. That literally prevents the motor from ripping its own valve apart.
Okay, but what if a valve gets sticky? A standard control signal might not have the juice to push past that friction. Enter the positioner. This thing acts like a localized brain, communicating directly with the muscle. It's constantly measuring exactly where the valve stem is, comparing it to where the main controller actually wants it to be, and then independently cranking up the air pressure until that valve is forced into the absolute perfect position.
right? But all these pneumatic muscles, these air-driven valves, they're completely useless without a constant supply of highly pressurized air. And what about all the specialized gases flowing through those miles of piping? Like, what is actually generating all that pushing force?
That brings us to part 3, compressors, the beating heart. Now, there are a few ways to compress gas, but positive displacement is arguably the most fascinating. It's not about blowing gas really fast. No, it's about physically trapping it in a room and then literally shrinking the walls of that room until the gas is just squeezed into submission. It is brute mechanical force at its absolute finest.
And this whole process creates this continuous mechanical heartbeat. This is the loop of a reciprocating compressor. First up, the intake stroke. A heavy metal piston pulls back inside the cylinder, creating a vacuum that just sucks the gas in. Second, the compression stroke. The piston violently shoves forward, trapping that gas and crushing it into a tiny space. Finally, the discharge. The pressure inside becomes so incredibly intense that it literally overpowers the heavy springs holding the exit doors closed, blasting the highly pressurized gas out into the plant. Thump, thump, thump. It's a continuous, tireless industrial heartbeat. And engineers love to stack these beating hearts to really push the limits. If you need insane amounts of pressure, you go with a multi-stage configuration. The gas gets compressed in one cylinder, then immediately fed into a smaller cylinder to get compressed again, and so on. If you need volume instead, you use a double-acting setup. That's where the piston compresses gas when it pushes forward, and then compresses a whole other batch of gas when it pulls backward. And depending on how cramped the factory floor space is, engineers can arrange these massive cylinders in tight V-shapes or L-shapes just to make it all fit.
But there's a pretty serious catch to all this violent squeezing. Compressing gas generates immense amounts of blistering heat. It causes moisture to condense into water droplets, and it often picks up lubricating oil straight from the compressor pistons. If you send hot, wet, oily gas into delicate plant instruments, you're going to destroy them. So how does the plant clean its bloodstream?
Let's get into part 4, filtration and drying systems.
The physics they use to clean this gas, honestly, it's brilliant. First, we use intercoolers, which are basically giant water jackets, to absorb all that dangerous excess heat. But to get the actual liquid out, we use demisters and oil separators. These clever devices use the physical weight of the liquid against itself. A demister takes the gas and spins it in a literal mini tornado. The heavy water droplets get flung to the outside walls by centrifugal force and slide right down to a drain. Oil separators, on the other hand, force the gas through a confusing maze of metal baffle plates. The lightweight gas can easily weave through the maze, but the heavy oil droplets, they can't make the sharp turns, so they just smash into the walls and get trapped.
And when that gas needs to be bone dry, zero moisture, the plant uses a desiccant dryer. This thing literally mimics the continuous rhythm of breathing. It uses 2 towering tanks filled with moisture-absorbing chemicals like silica gel. The gas flows through the active tank, getting scrubbed completely dry. But eventually, that chemical gets totally saturated. So, at the exact same time, the plant is blasting hot air through the second regeneration tank to bake the trapped moisture right out of it. When a timer goes off, mechanical valves just flip the airflow. The wet tank starts baking, and the freshly baked tank takes over drying the gas. It just breathes back and forth endlessly.
Bringing us to our final section, the ultimate industrial symphony.
When you really take a step back, you start to realize that this highly complex orchestration, the sensory network tasting the fluids, the pneumatic muscles firing the valves, the mechanical hearts compressing the gas, and the kidneys filtering out the moisture, all of it is entirely hidden from our view. Yet this invisible industrial anatomy is the silent partner behind almost every single manufactured product you and I interact with on a daily basis. It really is fascinating when you pull back the curtain. So the next time you grab a plastic bottle, flip on a light switch, or pump gas into your car, I want you to ask yourself, can you hear that mechanical heartbeat? Can you picture the artificial chemical senses and visualize the pneumatic muscles that all worked in perfect, tireless harmony to breathe that item into existence? Thanks for joining me on this explainer, and keep your curiosity activated.